That's fine. Oh, looks like you have a jacket. Well, please have a seat. Paulina, panel time. Yeah. Is Jake Abernethy in somewhere? Oh.
He's going to appear behind the curtain.
Yeah, can you text him? Say it would be fun to have him around.
He's coming at 5. It's 4:59.
Oh, okay. That's what he said? Hey, Jake, that's for you. All right, let me just grab my notes. Okay, all right. So it's been a long day, so we'll try to finish this with some entertaining panel. So first, let me present all our panelists again. So we have on the left will be Niao He from UIUC. We have our special mystery guest, Volkan Sever from EPFL. We thought it would be interesting to have him around because he always has opinionated positions. Jake Abernethy from Georgia Tech. We have Paulina Granova from ETH, something like that. And we have Kostis Daskalakis from MIT. And so I think just to start, perhaps you could each spend just 1 minute presenting what are your, like your latest interests on the topic of this workshop, like anything that you think would be relevant. So Niao will come. We'll start.
So I'm Niao, and as I was talking this morning, I think my recent interest towards this GAN-related work is really how we can actually formulate or revisit a lot of interesting machine learning applications from the GAN perspective. And hopefully, we can have better understanding with GAMs and also with better understanding with many other fields like reinforcement learning, Bayesian inference, and many others potentially. Yeah.
My interest in this is, distributions, learning distributions is a ton of applications. And I think the underlying problems are interesting challenges for optimization, where my interests lie. That's how I got into this.
That wasn't very opinionated. That was very natural. Anyway, I'm Jake. I did my PhD in online learning. A lot of my PhD was on online learning, and which is a cool set of results and stuff. But we never could find any good applications for that stuff, or they're kind of simple applications. But suddenly, all of a sudden, there's been this emergence of posing machine learning challenges as games, and that's been very exciting. And it's like added these questions of like, how do you do that? You're not just minimizing a single function. You're trying to find an equilibrium, and all of a sudden the questions of, how do you find those equilibria and what are the fastest ways? Suddenly all these old tricks in optimization don't really apply anymore. You have to use a lot more, develop new techniques, and it's amazing, like simple zero-sum games. We don't really understand the dynamics of how to solve those in the most quick way possible and under various settings. So I think this really is an exciting times for this sort of class of ideas and class of problems.
I'm interested in the optimization and evaluation of GANs. So as I said in my talk, these problems are very different than the likelihood case. And I'm interested in how we can use some techniques from online learning and game theory to tackle these problems in GANs.
So I'm coming at it from various perspectives. So on the from a broader perspective, I think min-max will be important going forward. So as Jake mentioned in his talk, and I also mentioned at the beginning of my talk, but Jake wasn't here. So I think as we make more complex ML systems, we need other ML systems to check properties of our ML systems. So this game playing between ML systems will actually become more and more important as we go along. So we need to understand various aspects of how to build frameworks for doing this. So on the theoretical from theoretical viewpoint, so I'm coming at GANs from I guess two perspectives. So one is the complexity of equilibria. As you know, in my PhD, I worked on the complexity of computing Nash equilibria. And here we have a very interesting case of zero-sum games. So zero-sum games are good games, but we have a special case that is like a very interesting case of zero-sum games that is actually not easy. So understanding the complexity theoretic ramifications around computing equilibria, I find a fascinating problem. I also find fascinating the high-dimensional distribution learning aspect of the problem. So GANs are trying to learn high-dimensional distributions. We know from a statistical point of view that learning high-dimensional distributions that are not parameterized from a well-behaved class is a very hard task. So building the right frameworks to make that happen is a very interesting problem.
All right, thank you. So let's start already for a bit of controversy. So one of the goal of this workshop was to bridge several communities together. So we have online learning people, game theory, and math programming. I was a bit surprised to see these optimization convergence results for like billionaire games, for example, from 2013. And I was not sure what was the contribution of this work compared to, say, just standard extra gradient from the 70s or fictitious play algorithm from the 50s. So what was the... That was too much. So what was the... do you know what I'm talking about, or...
Well, I think we're waiting for a question, maybe.
Well, yeah. What was the contribution? That was the question. So what was the was it just reinventing the wheel in a different community, or was there actually a different perspective and some practical, consequences from this perspective? Well, Costis as well might be aware of this. I don't know.
Let's see. So I'm not sure. So your question is why not use older methods?
I don't know. Like for example, I think in your talk you had this result by Sacha Rachlin and all 2013. So what's different there than just plain old extra gradient could be used to solve this billionaire game?
So
and perhaps
are you asking Jake about the work of Sasha, or?
Well, he cited it in his talk, so I don't know. But Volkan can jump in.
Yeah, sure. I mean, so you understand that they're trying to look at a scenario where it's not an optimization problem, right? In the end, there is like two players, and you care about regret of these players. Like GAN problem, the way we set it up, it's actually not in my opinion, it's a synthetic game theory problem, because you don't care if the discriminator suffers any regret at all, as long as you get the saddle point, right? So the setting that they've done, and what Costas had as a challenge was that, if you know that there are two players that are in this minimax matrix game setting, right, and that they kind of cooperate, they have a predetermined strategy, then they can reach to the Nash equilibrium at a fast rate while having optimal regret on both sides. So there you actually care if an individual player suffers, right? In the way we write the Wasserstein GAN, you really don't care about this, right? So the subtlety about characterizing the regret, et cetera, there is very novel. The optimistic mirror descent, and so on and so forth.
So let me make one comment. So what's interesting about solving a zero-sum game, a bilinear game, you have player X choosing from a simplex and Y choosing simplex. You can solve that problem using linear programming very quickly, with log
Small
1 over
dimension.
epsilon dependence, right?
In very
So-
small dimension.
Sorry?
In very small
In very
dimension.
small dimension. Okay, so I guess the dimension becomes an issue there. Sure. and in some ways, that kind of made it seem like it wasn't interesting to try to treat this as a decoupled two-player game where you had a sequential process with two players updating strategies and storing their iterates or the average iterate. And I think for a long time it was sort of, that was the fact that you had this linear programming solution was sort of discouraging. I said, well, don't worry about these online learning methods. They don't actually provide that much value. I think more recently we've seen that actually, no, that is a very good approach to thinking about solving a zero-sum game, because once you get into scenarios like GANs or more complex games, there isn't an obvious way to reduce this to a single one-parameter optimization, or just minimizing a function f of x over some convex set. It's much harder to it's much easier to describe it as a decoupled process where you're trying to find a min-max. So I think that it's been clear more recently that this decoupled perspective where you actually do treat the two players differently and you have them communicate only having small amounts of communication between the two players in a repeated process, that is actually a very natural way. And the fact that there hasn't really been that much development on the original GAN idea. The original GAN idea where you do simultaneous gradient descent, from my understanding, there have been small tweaks to that, but roughly speaking, it's not like I haven't seen anyone reduce this to a single minimization problem. We haven't seen that be the way to interpret the training of a GAN. So I think it's quite natural to view it as a decoupled process. I'm guessing you have some thoughts as well.
Right. So I guess the straight answer to your question about Sasha's work is that optimistic FTRL actually gets you the best of both worlds. So if you're playing against another player who's playing the same game as you get 1 over t regret. If you're playing against nature, who has he's not playing the same game, who's trying to punish you, you get 1 over ut. So the realization in that work was that you can get the best of both worlds. In fact, I had a paper before Sasha where we did this 1 over t, this best of both worlds. There we actually used, we basically created a no-regret learning method out of the excessive gap technique, which was more complex than the optimistic FTRL. But ultimately, the realization in this line of work is that. And in fact, already going to fictitious play, right? So the realization is that playing against another player who's playing the same game as you is more of a dance around the equilibrium, whereas playing against nature, things are harder. So this sort of like fictitious play converges against another player playing fictitious play, but does not converge against nature. In this line of work. You get 1 over t versus 1 over ut. That's the contribution there that I guess was not known before.
Okay, thanks for this clarification. So another topic that we touched, that was a bit touched implicitly. So some talks were presented with the zero-sum game, the min-max formulation. Other talks mention the more general, like non-zero-sum game where you have multiple players or even variational inequalities. So I'm a bit lost now to which results apply to which setting. So in particular, a concrete example would be your talk, Paulina, where could you also use the same techniques for non-zero-sum game, this duality gap, or now it all breaks down? So my question to you would be, what are your thoughts about this difference between non-zero-sum game versus zero-sum game? What is different? What is still open, etc.?
So I think of course the topic is so rich that several of us are coming at it from different perspectives. So my personal perspective on GANs is that it's not a game, okay? It's a min-max problem. So for me, the inner player is computing a distance between distributions, and the outer player, the generator, is trying to minimize between his generated distribution and the real distribution. So in that sense, sort of for me, there's just one objective, and the two players care about the same objective. Now, we heard about several interesting ideas for including maybe the very last talk, where you may have multiple objectives that you're optimizing. Also, there are hacks. Starting from the first paper on GANs. There were hacks that were introduced because you got very small gradients in your training, And these hacks resulted in the two players having different objective functions. So, so again, it depends on how you're coming at it. So for me, it's not a game. It's minimizing distance between two distributions, but different perspectives or hacks on the main idea may give rise to different objective functions. And of course, like the more and that reflects my book. The more you deviate from like the zero-sum setting, the more you're gonna hit a complexity wall. Okay, so.
So when you say for you, you mean that all the work which still do generative modeling, but with non-zero sum, you just say, well, let's ignore this, or this is not.
Excuse me, what?
Because you say for you, GAN is a min-max. So
right.
what I'm saying, I mean, in the literature, there's actually a lot of formulations which are not min-max. They're
right.
brought as just non-zero sum two-player games, and actually you can even have more than two players if you want. So you're just saying let's ignore that, or what?
No, I'm not saying that. So I'm saying
you prefer to focus on the min-max.
No. So I guess the later use of for me was sort of like for me coming from the complexity theory point of view, where the more you deviate from zero-sum games, you get harder problems. Now, but you mentioned something interesting. So the multiplayer version of the problem, and I think that's a very interesting one going forward. So, like in this complex world that we may envision for the future, where we have different ML systems interacting with each other and taking upon each other's properties, you may envision a world where like it's not two ML systems playing a min-max game against each other, but like several of them, trying to exploit each other or guide each other in doing something good.
Anybody else wants to chime in on?
Yes, for GAN specifically, I do see them as zero-sum games. And the theory we have depends on the zero-sum games. We know that in practice, for GANs particularly, the original formulation is zero-sum with the non-saturating update rule for the generator. But in practice, we do use the non-saturating rule. So what we did in our experiments for when we trained with the non-saturating update rule, we evaluated on the zero-sum formulation of GANs. And that works well in practice. So
the duality gap was evaluated on the actual zero-sum version, even though you get the pairs. Okay.
Yes, so some of the models are trained with the saturating, some are trained with the non-saturating, but for both cases, we use the min-max formulation for the evaluation. Yes.
Neo, you wanted to add something?
I think one of your questions was like we have lots of results for zero-sum games, non-zero-sum games, even multiple player games, right? So and how which results apply to which. And as I mentioned in my talk, all of those problems, either is zero-sum or non-zero-sum or two-player or multiple-player games, they all can be characterized as variational inequality problems. So any result for variational inequalities applies to those special cases, I would say. But one should be careful with like what is the optimal complexities for each of those special cases, because for general problems, you might get worse optimal complexities. Say, for instance, if you consider a convex-concave saddle point problem, and if you apply mirror-prox algorithm, or even if you consider a matrix, like bilinear matrix game, we know that mirror-prox algorithm actually gives you the optimal convergence rate, which is 1/t. However, if you apply mirror-prox to a convex minimization problem, you only get like 1/t rate, which is known to be not optimal because Neserov's accelerated algorithm gives you the optimal 1/t square rate. So there is a gap there, although both of them can be characterized as variational inequalities, and you get the 1/t rate from variational inequalities, but some might be optimal for some special cases, some might not. So we need to be kind of careful with that part, I'd say, because when we solve a general problem, it's kind of a nice framework, but we might lose some of the structure, underlying structure of the problems that we're dealing with. So if we are really just solving a zero-sum two-player game, you may want to kind of apply algorithms that are pertained to min-max structures, say, for instance, primal dual algorithms, rather than a general variational inequality algorithm. Or if you are really solving a Nash equilibrium problems, yeah, I think you can apply like variational inequality type of algorithms because there doesn't exist any primal dual algorithms anymore in those situations. So that's kind of my opinion there.
Yeah, I mean, so just to reinforce this message, I hope it is clear that there are cases where the problem is written minimax, but it's not a game per se. There are no two players that are somehow competing. It's an optimization problem. Given the optimization problem, you can look at the relevant optimization literature and pull out the optimal algorithm. And now some of these problems are non-convex, which is kind of creating these new challenges, which is fine. But I mean, for example, Kostas mentioned this multiplayer games with systems playing each other. That is actually a good game, right? Now, what is interesting to me is to see online optimization and regret minimization algorithms now being applied to pure optimization algorithms. And somehow these characterizations of the dynamics are providing new insights as to the behavior of the algorithm for a non-convex, let's say, landscape. To me, this is very interesting, right? So it just somehow says that, this, minimum regret algorithms generate these dynamics that are somehow well behaved even in the non-convex setting. I think this is some topic to pursue and learn from. But like, if you have a optimization problem in a minimax form, just use mirror prox, then don't worry about it.
So what are the guarantees of mirror prox for non-convex min-max problems?
That I don't know.
So why do you want us to use it?
I mean, that's why
instead
in my
of,
talk,
say, negative momentum.
I try to say that, convexify the problem, right? Use the insight from the mixed Nash equilibrium and say, hey, let me just try to find a distribution over generators so that my problem is well posed. I'll apply an algorithm that I know is going to work, right? Then I reduce the problem into,
A different problem.
Yeah, you shift the difficulty to something else. No, but I mean, what am I going to do? I can talk about variational inequality and give you unverifiable assumptions a priori for the working, to guarantee the result where the algorithm works. So I can talk about dissipative properties, assumptions, but can you verify them? That's the problem, right?
So I guess one of the outcome of this is big open problems are how to generalize all these results to non-convex aspects. So already we had some interesting work from Paulina, where it was I guess you call it semi-concave, semi-shallow. Yeah. So I think I have also a bunch of other questions from the panel, but I would like to open it up to the floor. If there are any question to our panelists or comment about the day, it doesn't have to be a question. It can also be a comment. This is like a workshop for people to brainstorm together. Anybody wants to intervene? Otherwise, I can just... we have one over there. And we'll have Yanis doing a bit of sport. That was slow.
So I haven't worked with GANs myself, but here's a thought. Because there's oscillatory behavior, why not just average the iterates, right? Because several algorithms use averaging of iterates. Why not actually do it in practice? Any thoughts?
Well, actually, I have an answer on that. So
yeah, there's probably lots of thoughts to this. It really is a challenge with when you're in non-convex settings to do averaging. My talk today, I mentioned, the standard tricks when you're in convex concave is Jensen's inequality. You get Jensen's inequality. Take the average of the function values as a function of the average value. That's great. That's really useful. As soon as you leave the convex world, you don't have that anymore. It doesn't make sense necessarily to average. Averaging parameters or neural networks is, I've never heard anyone say that was a good idea. I could be wrong. I don't do a lot of implementation. Is it a good idea? I wasn't in your talk, sorry. No.
Yeah, so there's
averaging
there's a lot of empirical evidence now. So we actually have a paper on this.
The question is what kind of averaging you're doing. That's the question, right?
So
what do you mean by averaging? Right?
Yeah, so just uniform average already helps. And actually you can look at, there's a lot of papers now in GANs who use just simple average. But indeed, because it's non-convex, it doesn't make that much sense to do the full uniform average. So
I think Tong Zhang has a paper on averaging, on some kind of a functional averaging, which you can do. And maybe there's some way to do that efficiently. I haven't read that in super close detail, but I think it's an interesting question. Somehow when you do in these game settings, taking average of your iterates along the way is like a kind of a critical tool that doesn't naturally work well in non-convex settings, even though it sounds like there's more thoughts that I should wait to hear.
Yeah, so I'm not necessarily against averaging. Especially if you do it the right way, not keep around too many generators and averaging them. So So ultimately, you'll do what works, right? So, the call for action is, get me an algorithm that goes to, has stable behavior in the setting, okay? I don't find averaging, like Jake, I don't find averaging elegant and or justifiable in a non-convex setting. But if you can get me convergence guarantees, hats off to you.
Add a few words about averaging actually, because I think even in the convex concave case, there are lots of confusions with how to take average. Because lots of the standard approaches, like we can take uniform average, or if we just take the weighted average using the step size. And we know usually we use decaying step sizes, meaning that for the the newer iterates, we're using smaller step size, which is actually counterintuitive because in general, you would hope that for the more recent updates, you will put more weights on those updates. In fact, there are actually lots of work on how to use general averaging schemes and how to show convergence bounds of that. And those are well established in the optimization literature, but it's just people tend to ignore it and because the theory is complicated. But I would say there are very well established theory on how to choose those step size or choosing those weights, and there are also adaptive strategies for how you can choose those averaging. So I have to say it's actually, there are lots of opportunities with averaging, and we should not just say, okay, this is not a good idea for non-convex case.
But did you say there was a well-established procedure to choose these averaging weights?
Yes.
Do you have a citation for that? Because all I was knowing were these weird average of the step size, which doesn't make any sense.
Sure, yeah. So for instance, let's just take the mirror prox for example. How you characterize the optimality really determines how you pick a good certificate, right? And the way you pick a certificate to characterize bound, you can take different averages. And really the algorithm has nothing to do how you take average. It really depends on how you choose a candidate solution. And a good reference I would point out is one of the paper by Nemirovsky, I think in 2000. And there is a very, very nice summary of for general weights, which they call it as a certificate, and how you can provide a general bound for any as long as it's a convex combination, you can give a good bound for that. And that implies that indeed you need to choose larger bound for the more recent updates. And that's the better strategy, yeah.
Thank you.
And there are also lots of work by, I think, Angelia Ledich on how you can actually optimize the weights or how you can adaptively choosing those weights in at least for stochastic gradient descent. But I'm not sure if they have solutions for solving general variational inequalities, because there I think it's more tricky because you have a dual minimization dual problem there, and how to optimize the weights might be a little bit more tricky there. Yeah.
So we had Octavian had a question.
I just wanted to add a small comment. So if you're familiar with language models, so state-of-the-art language models from the last year, past year, so they are essentially models with millions of parameters, around 20 million parameters, and state-of-the-art optimization tools for that one are really SGD in the beginning with constant learning rate, and then from some point on switch to averaged SGD. And that gives you always a boost in perplexity loss. So perplexity is the loss function used for language models. So I've personally tried playing with that, trying Adam and switching between this. And it's Adam, for example, is always much, much worse.
But this is a maximum likelihood training, or it's actually a game?
Yeah, no, sorry, it's just maximum likelihood. I should have mentioned that.
So it's standard optimization.
Yeah, exactly. But it's highly non-convex since you have 20 million parameters. So you're talking about
yes.
Boost in the generalization. It's actually both the training and the test loss who get a huge gain once you switch from SGD with constant learning rate to average SGD. Yeah, thank you.
No, I mean, I don't have anything to add.
No,
to
it
this.
was just so that you hold the mic. Somebody needs to hold the mic. Unless you want to add
I'm not
something.
opinionated. I'm not. Let
Um,
me set the bar.
so perhaps in the back, Yonis, you want to do some exercise?
Oh yeah. Where are we going? Okay.
I am an optimizer, but I still want to make this optimization or whatever game theory useful for practice. Now, my question is, well, of course, we can frame many theoretical questions like convergence or convergence rate or complexity, but there's definitely a large gap between theory and practice. And what are the strange phenomena you have observed in your practice that you cannot explain? That our theoreticians really can make a difference. That practitioners will say, oh, the theoreticians really explain something I cannot understand.
Exciting question.
Well, that's a pretty broad question you're asking. So I could, many ways you could answer that. But in the context of GANs, I do think that is Sanjeev here? Sanjeev Arora is here? No. Sanjeev's paper on mode collapse from at least a year or two ago, I think, was quite instructive as to people were saying mode collapse was a problem of maybe some just training problem, something about this gradient descent procedure, and they pointed that actually it can be described just through the lens of VC dimension. There's just a VC dimension problem. If you don't have enough complexity in your discriminator class, you're going to guarantee that you're going to have to have mode collapse. And I think that was actually somewhat instructive and really did give a good perspective on what might be happening. But maybe others have other thoughts. Okay. Next question.
So actually, Gutsi has a question. But yeah, go.
Okay, so we talked a lot about converging to Nash equilibrium, but it appears that like in non-convex games, we can converge to points which are like locally stable and which are not Nash equilibrium. And so I just want your opinion on that. Like, is it a bad thing or like we don't care actually? We're just looking for a stable point.
Can somebody also at the same time define what a stable point is for the audience?
It's just a point where like locally we converge to it.
So to repeat, a stable point is a point such that locally you converge to it. What do you mean by locally you converge to it? You mean following gradient descent?
For me, it does not need to be minimax, but if you start the algorithm there, it'll remain there.
Which algorithm?
So local perturbations.
Okay, let's have
So the
Costas
main
define it.
definition-
Somebody rigorous.
The main definitions of stability, but roughly speaking, a point is stable if there is a small, like for a ball of small perturbations around it. If you follow the dynamics, they'll get you back there.
Which dynamics?
So stability pertains to specific dynamics. So if you're talking about stable points for gradient descent, we're talking about those dynamics and so on and so forth. But not to answer your question, that's right. So. As we saw in at least I think a couple talks, maybe yours and mine, or maybe more, gradient descent ascent dynamics in min-max problems with non-convex concave objectives could go to stable points that are not locally minimax. I think this is a bad situation. I think it's even a bad situation if it goes to a locally minimax but not globally minimax point, because the setup of a GAN is basically again the inner soup player is trying to compute a distance. If you go to a locally minimax solution, all bets are off about how good of a job the discriminator is doing in comparing your distribution against a real distribution. So I would feel uncomfortable about even a locally minimax but not globally minimax point. And I think as far as learning how to generate interesting complex distributions is concerned, we have to pay a lot more attention in how we architect our GANs to actually help the discriminator and the generator in getting to globally optimal solutions. And I feel that like in an effort to come up with such architectures, we also resolve the huge statistical issues that underlie training a GAN. So, training a generator to produce reliable distributions that are high dimensional is not going to just happen. Okay, you cannot just expect the generator to reliably generate 1,000 pixel distribution if you do not make some modeling assumption about the lower dimensional structure that would enable this learning to actually take place on the first place. So I feel like like the statistical aspect and the optimization aspect have to come hand in hand in architecting the generator and that discriminator, or possibly, as I mentioned in my talk, a collection of discriminators that are solving different little discrimination tasks in order to both help the optimization, but also the, as I said, hugely important issue of curse of dimensionality that we're facing here.
All right, another question I had was, in order to bridge the communities, do you have any recommended surveys, perhaps, for somebody who would like to get insights from game theory, or getting insights from math programming, or perhaps also how to get more insights about GANs?
I mean, there's the classic book. Is Nicolo here, the chair of the? I'm just going to. I'm going to compliment the chair of the conference now. There's the classic book of prediction learning in games that came out in 2006, which I think has a really good broad overview of online learning methods, and many. There's a whole chapter on game theory applications there. Since that book came out, there have been some slightly more modern treatments using online complex optimization tools, which also exist. But I think that book really is an excellent starting place for folks who want to learn more about just the conceptual framework behind regret minimization. That book came out right when I started my PhD and really did launch a lot of my future research. So thanks to Nicolo for that. What else?
Yeah, so if you are Volkan was speaking of Arcadi's book, but so if you're looking for like really just the variational inequalities, first of all, if you're just looking for like how you can view like lots of games as a variational inequality framework, I would highly recommend a very short survey paper by Zhongxi Pan and his co-authors. I think that one characterizes or contains a lot of detailed kind of characterization of different problems of convex structure into variational inequality. As Volkan was speaking just now, I think another thing also Paulina was talking about was how you can actually characterize the accuracy, or how you can actually propose a certificate to evaluate how good your accuracy is. What is a good accuracy measure? And Arcadi has a very nice paper on accuracy measures for variational inequalities, which kind of provides a unifying framework to characterize accuracies both for minimization problems, min-max problems, as well as variational inequality problems, and also Nash equilibrium problems. And I think that's also a very nice survey paper.
Do you have the rough title or a year for this paper?
The rough title is Accuracy Measures for Problems with Convex Structure.
And the first paper you mentioned, what was the author's name?
The author's name is Zhongxi Pan and Aldo from Purdue, and Zhongxi is from South California, So they're kind of experts in variational inequality.
One more comment. There's a book called Learning in Games, I believe, and it's by a couple of folks that are from, I think, the econ world. You know what book I'm talking about? Learning in Games? I think by Fudenberg and Levine, maybe? Fudenberg and Levine. One thing I find that all of a sudden, all these machine learning people have jumped into the world of game dynamics, and I do want to remind people that that has been studied for a long time by the game theory community and the econ community. And I just, as a word of caution, it's good to get familiar with like what people were thinking about in, let's say, the 80s and the 90s and 2000s, because this is not GANs was not the first time people were interested in game dynamics. It's been going on for a long time. But these folks aren't in our community, so we don't tend to interact with them as much.
But are these continuous games or discrete
these are continuous.
games?
Well, they analyze. They do some. I have to remember now. I haven't looked at the book in a little while, so I'm actually guilty of this as well. But I do own the book. So that's something, right? It's a start.
It's to pose.
I think my grad student stole it from me or something. I haven't seen it on my shelf recently. Kevin, you have it, don't you? Yeah. Anyway. But yeah, I think there are other surveys that I've seen. I've actually gotten a couple of papers out just by going back and looking at some of the work that game theorists and economists have done, and it's been very helpful. So I do recommend folks to take a look at that literature, and he knows it better than I do.
Yeah, but I wanted to comment on, we have heard a lot of references for learning in games and optimization. However, I'm going to say that again, we are missing high-dimensional statistics references. So, as I said, that learning, difficult distribution is not going to happen by accident. So we have to model our data.
So we have an intervention over there. Yeah. Over there. Thank you.
So one thing I was wondering about is the kind of generalization error component of the games that we play. So, in the non-game theoretic setting, we've have a long history of looking at the difference between one's training error and generalization error, either from a learning theorist perspective or Bayesian's perspective, or however you might want to choose. In the games that we're talking about here, one of the players, at least, is often a data-driven player in that game. They have some limited information, and underlying that, there's also some true objective that they don't actually have access to. Are there handles on how we can best deal with that? Because that, in a GAN, for example, that dynamic really affects what happens in the GAN, because in a certain sense, it's much easier for the discriminator to tell whether something is off-manifold than if it's to tell that it's not capturing the tail of the distribution, because it needs a lot more samples to do the latter. So these issues affect the dynamics in these sorts of games, probably affect the underlying formalism for that. Are there ways that we can handle that at all in this sort of setting?
Yeah, so usually when the GAN objectives are set up, you take a sample average that is replacing expectations, and there's, in the high dimensional setting, there is, already there you're introducing a lot of error that I haven't seen a serious study of. So, like you can go, the VC dimension route, but that's going to be too pessimistic. And, you probably won't have enough data to actually substantiate that it's okay to make that swap from expectation to summations. And again, going back to what I was saying earlier, I think the only way to address these high dimensionality issues is to architect the GAN in a different way, like more modularized, so that you do not encounter all of a sudden, getting in your lab high dimensional samples that you have to argue about. Okay.
There are other challenges to this. The samples you take are also, typically you assume IID if you want to give deviation bounds, but in reality, if you're working with real data, it's not, right? That leads to inherent biases and so on and so forth, which is like a major topic in machine learning currently. So many of these things are tied. I'm not sure if it is as easy as just configuring the GAN to capture and allow us to get to the global minimum of whatever we defined, right? The deviation of the risk function that we're optimizing from the true one also matters a lot. So there we also need to be careful about how the samples are also taken.
think on those wise words, that might be the end of our panel. I want to leave enough space for posters and coffee and everything. So perhaps let's thank all our panelists again. So we'll post all these wonderful references on the website as well. We'll post the talks and now there is a poster session until 6:30 roughly. So enjoy the rest of the day.